Buffers are a really important component of working in almost any laboratory setting. And so understanding qualitatively how to prepare them and then quantitatively how to do the calculations so that you can physically prepare them are really important. So this problem, SAM problem 19.3, says an environmental chemist needs a carbonate buffer of pH 10 to study the effects of acid rain on limestone-rich soils. How many grams of sodium carbonate must she add to 1.5 liters of 0.20 molar sodium bicarbonate to make the buffer? And they give us the Ka value of the bicarbonate ion as 4.7 times 10 to the minus 11th. So a couple of things to think about with buffer preparation is you want to think about the buffer system that you want to use. Now in this case, they've actually already chosen the buffer system. So I just want to make a comment about the buffer system in case it wasn't something where they actually gave you the buffer system. So remember, a buffer is always going to exist of a weak acid and its conjugate base. And hopefully we can see from the solution that we have here that they give us sodium carbonate to work. Remember, all sodium ions are soluble, so what this really means is that we've got sodium ions, which we're not considering, and then carbonate ions. Oops, I shouldn't circle that, that's important, but carbonate ions. So we've got carbonate ions. So that we get from the sodium carbonate. We also have sodium bicarbonate. All sodium salts are soluble, so again, that gives us more sodium ions in solution, which we're not worried about. And then bicarbonate, it's -2. So buffers consist of weak acids and their conjugate bases. So our weak acid is the bicarbonate ion, our conjugate base is the carbonate ion. So if we were to write an equation, bicarbonate in water gives us H3O plus and CO32 minus, and then again they gave us the Ka for this as 4.7 times 10 to the minus 11th. So they actually already gave us what our buffer system is. But I want to show you that they actually did choose the correct buffer system. So if this problem was such that you didn't even know what buffer system you wanted to choose, you need to choose a buffer system where the pH that you want to be at, so the pH to be at is plus or minus 1 of the pKa of the weak acid. So again, I just want to show you that that's actually what they did here. So again, the pKa, we can take the Ka, the negative log of the Ka value gives us pKa, which in this case is going to be equal to 10.33. That is within plus or minus 1 unit of our pH, so that is something that's going to be fine for this. So not part of this problem, they actually made that choice for us, but I wanted to prove to you that that was a valid option. And if you didn't have that in the beginning, what you need to do is find a weak acid conjugate base pair such that the weak acid that you're choosing has a pKa that's within 1 unit of the pH that you want to be at. Okay, so again, our weak acid we're going to be getting from sodium bicarbonate. Our conjugate base we're getting from sodium carbonate. So what we really need to do is we're not going to be at pH 10.33. And hopefully this makes sense. I'll show you in a minute. If we wanted to be at pH 10.33, we actually have equal amounts of both of them. We don't want to be at 10.33, we want to be at 10.0. So we want to be a little bit different from that. So what we want to be able to do is use the Henderson-Hasselbalch equation. And one thing to just kind of show you here, when we were talking about quantitative aspects of buffer kind of on our sheet here, talked about using the Henderson-Hasselbalch equation, which is right here. We can use it to calculate the pH when you know these concentrations, and we used that in sample problem 19.1 when we wanted to figure out the pH of our buffer solution. But we're going to use it in this context, to use it to calculate the amounts of weak acid and conjugate base to prepare a buffer at a given pH. All right, so second part, so we chose our buffer system. The second part is we need to figure out, well, how much of each do we need? And we can use the Henderson-Hasselbalch equation for that. So again, the Henderson-Hasselbalch equation says the pH is equal to the pKa plus the log of the conjugate base concentration over the weak acid. Do you remember I just said a second ago, if we had equal amounts of our conjugate base and weak acid, we would be at pH 10.33. And that is, again, if these are equal, this is a 1, the log of 1 is 0, so this term drops out, and pH is equal to pKa. So pH would equal 10.33 if we had equal amounts of these. Well, we don't want to be at 10.33, okay? pKa is, again, 10.33. We want to be at 10.00. So we need to know what's the ratio of these guys that we need to have such that we decrease the pH a little bit. Now, we've already kind of talked about some things a little bit. We want this term to be a little negative. So we want this to be slightly negative, right? Because we want to diminish the pH. To be slightly negative means we need to have a greater amount of our weak acid than our conjugate base, right? Hopefully that makes sense. We want this ratio to be less than 1. We want a greater amount of our weak acid. Well, some of the information they already gave us, they tell us that our weak acid concentration is 0.20 molar, right? We've got 1.5 liters of 0.20 molars. We want to know how much do we need to have our conjugate base concentration be. And we're going to have that because we're going to be adding grams of sodium carbonate to make that. So again, if we put kind of some numbers in here, we're going to have 10 equal to 10.3, and I'm going to keep some significant digits here, 10.3279 plus the log of our conjugate base concentration over 0.2. So again, the weak acid concentration, they told us, was 0.2. And we want to know what does our concentration of conjugate base need to be such that this ratio will be subtracted from this to get us to 10. So we can get rid of, we've got a combination of terms over here, so 0.3279 equals the log of the conjugate base concentration over 0.2. If I want to get rid of the log term, I can take 10 to the, and make sure, some people were getting confused throughout the course here whether they use the E or the 10 function. And make sure you see on your calculator too. In my calculator, these two are right next to one another. I've got log and I've got ln. And we kind of both, we say kind of log or natural log, but we can see that when we use the log, the inverse of it is 10 to the. When we use the natural log, ln, the inverse is e to the. So make sure that you're using the right function in your calculations and on your calculator. So taking 10 to the log of something gives you that something. So this is the conjugate base over 0.2. 10 to this number in my calculator gives me 0.47. We already predicted we wanted a ratio less than 1, and we do get that. But this will tell us that the conjugate base concentration is going to be equal to 0.0940 molar. So again, our conjugate base concentration is going to be equal to the concentration of Na2CO3, 0.0940 moles per liter. That's what we want our concentration of conjugate base to be at. But we need to actually figure out how much of this sodium carbonate do we need to add to give us this concentration. And it doesn't explicitly say this, but we're going to make the assumption that the volume to add, or the addition is, because this is a solid that we're adding, that the amount that we're going to add is not going to change the volume significantly. So we're going to assume the mass to add changes volume negligibly. So if this is the concentration we need to be at, we have 1.5 liters of solution. So we know we need to have 0.141 moles of sodium carbonate. And probably I should actually say that this is not really sodium carbonate. It's really carbonate ion. and I probably should not take a shortcut here, but show that when we have 1 mole of carbonate, that's equal to 1 mole of sodium carbonate. Because you're not going to find a bottle of carbonate to kind of weigh out in a lab. You're going to have sodium carbonate that you can actually mass and weigh out. So again, we're going to want to have this numbers of moles of sodium carbonate. We can use the molar mass here. 1 mole of sodium carbonate is 106 grams. And that's 14.946, rounded to about 15 grams of Na2CO3. So 15 grams in the context of 1.5 liters. Okay, and I guess to imagine that, imagine 15 sugar cubes. So if you think about the size of about 15 sugar cubes, it's not insignificant, but imagine putting that into about a 2-liter bottle of soda. It's not going to be overly significant, and we're going to assume that the volume change is negligible. If you're actually preparing this solution in the lab, what you do is mix stuff together, and then at the end, make sure your volume was about 1.5 liters. Okay, so 2 things to kind of consider with preparing a buffer. Choose your buffer system such that the pH that you want to be at is within 1 unit of the pKa of the weak acid that you're choosing. So you got to make sure that you're using the right system. Then you can use the Henderson-Hasselbalch equation to figure out the ratio of your conjugate base and weak acid you need to be at, such that your pH will be adjusted from your pKa value. Because your pH will equal your pKa value if you have equal amounts. So again, hopefully that problem pretty straightforward with thinking about how you can prepare a buffer.